Welcome to this video. In this video, we are going to look at how we can solve problems using the strategy of finding a pattern. And this video is part of a series of videos that's looking at different problem-solving strategies. Oftentimes when we're teaching students to solve problems in math, they can get bogged down in the wording of the problem and how to start a problem. So giving them a good toolbox of different strategies to use when they get to a problem and how to start tackling it is really important for students to have. So like I said in this video, that strategy that we're going to look at is finding a pattern. And as math is full of patterns, and not every single problem can be solved this way, but oftentimes problems can be solved by finding a pattern. So the first example we're going to look at is a pretty clear one where we're looking for a pattern. It says how many tennis balls will be in the 10th layer. So our hope is that we can kind of look at the pattern and figure out what will be in the 10th layer without having to draw all 10 layers, because I'm not a great artist. I don't want to have to draw that many circles. So let's see if we can find a pattern to be able to help us with that. So a good first step in finding a pattern is to draw a T-chart. I'm going to label one side layer, and the other side is going to be the number of balls in that layer. So we can see from our diagram there that our first three layers are drawn for us, and they have 1, 3, and 6 tennis balls respectively. And we could look at this and start seeing a pattern right off the bat. We could say, okay, it's going up by 2, then it's going up by 3. Probably 3 layers isn't enough for us to verify a pattern, but let's see a fourth layer. If this pattern continued, we'd say, oh, it would be going up 4. So our next layer should have 10, but let's draw it to confirm that. So our fourth layer would have our third layer and then 4 more underneath. So yeah, it's going up by 4, that's 10. We can give ourselves a thumbs up and say, okay, I think we found the pattern. The next step is to extend this pattern. We want to extend this all the way to know what our 10th layer will be. The long way to do this is using what's called our pattern rule. So that's the rule that we just found. We can do it this way, it's a little bit longer. And this rule is, we know, okay, we're starting with 1 ball. So we're starting at 1. It's a terrible 1. And then we add 2. But then each layer we're adding 1 more. So add 1 more each layer. All right, that is our pattern rule, and we could extend our pattern that way. All right, let's try that. Let's do it the long way. We'll see if I can have enough room here to do that. So 5 would then go 15, 6 would be 21, 7 would be 28, 8 would be 36, 9 would be 45, and 10 would be 55. So we can see that in our 10th layer, our pattern going up, starting at 1, adding 2, and then adding 1 more each time, takes a little bit of work, but by just some simple addition, we can see that the 10th layer would have 55 tennis balls in it. All right, and that's probably still easier than writing out all, or drawing out all the tennis balls. But I'm going to go back and erase a little bit. There's also something called an explicit pattern rule. And this is often, if it's harder to find, but if we can figure this out, it is easier to extend our patterns. We won't have to, it's not recursive, which means we won't have to know the one before it, right? To get to number 10, we had to know the 9th layer. To know the 9th layer, we had to know the 8th layer, and so on, all the way back to 1. That's called a recursive rule. In our explicit rule, what we're going to do is we're going to relate the number of balls to the number of layers. So what we're going to do is, can we look and say, is there a relationship between the number in our number of balls column and the number in our layers column? And this is a little bit tricky, but if you notice if you take the layer and the one before it, and you multiply those two numbers, what do you notice? So 2 times 1 is 2. 3 times 2 is 6. 4 times 3 is 12. And what do you notice? Well, if you look at 2, 6, and 12, I don't see that in the number of balls, but I see half of that in my number of balls column. So our explicit rule here is if we take our layer and we times it by our next layer, and we divide it by 2, we will get the number of balls. All right, and this makes it way easier to find our 10th layer, because we know to get it, we take our layer, which is 10, we times it by our next layer, which is 11, and we divide it by 2. So that's 110 divided by 2, which gives us 55. Same as we got when we did it with our recursive pattern rule, right? So it's a little bit quicker if you can find the explicit rule. It makes it a lot quicker to get the final answer, but it can be a little tricky and takes a lot of practice being able to try to find those explicit rules. So those are the first types of questions that you can solve by finding a pattern. The types of questions where you can make a chart and you can extend your pattern and find a recursive rule or find an explicit rule to find something down further in our chart. Let's look at another question that maybe isn't as much obvious as to why a pattern would work for this. So this question says, what are the last 3 digits of 5 to the exponent 2000? Now, a lot of students, they'd see this question and they'd go to their calculator and they'd put in 5 to the exponent 2000, and their calculator would get mad at them. Be like, I can't fit this in my little screen up top. It is too big. 5 to the exponent 2000 will have a lot of digits. It won't fit in our calculator. So we can't just evaluate it and look at the last 3 digits. So if I was starting this problem, I'd be like, okay, I can't do 5 to the exponent 2000, but let's look at some smaller ones that I can evaluate and see if I can see any sort of pattern that can help me. So remember, anything to the exponent 0 is equal to 1. An answer that a lot of students forget. Oftentimes they say 0. I'm probably going to do a video in the future about why anything to the exponent 0 is 1. But for now, just trust me. 5 to the exponent 1 is 5. 5 squared. 5 times 5 is 25. 5 to the exponent 3 is 5 times 5 times 5 is 125. And we can continue on doing that. 5 to the exponent 4 is 625. And we start by noticing, hey, all right, first thing I notice is that they all end in 5. All right, look at that. They all end in 5. Okay, there's some sort of pattern. And then we notice that, the second last digit is always a 2. All right, but the third last digit, well, I have a 1 and a 6, so that's not the same, but let's do another one. Let's do 5 to the exponent 5. So if you do 5 to the exponent 5 in your calculator, it can handle that one. It's 3,125. Okay, now we can see, all right, it's a 1 in the third digit. So if we extend this little squiggly yellow line, we had a 1, and our pattern still holds for the last 2. It ends in a 25, which makes sense because 5 squared is 25. So that can make sense in our minds of why it ends in a 25. But let's do one more. 5 to the exponent 6 is 15,625. So we now start to see this pattern emerge that the last 3 digits are either 125 or 625. So the question is, when is which? So if you notice here, the ones that are 625, they are even exponents. And if you want to test that, go put in 5 to the exponent 8. It's 390,625. Okay, so that pattern continues. And it looks like the odd exponents, 3, 5, we can check for 7, 5 to the exponent 7, ends in 125. So if it's an odd exponent, it ends in 125. So now 5 to the exponent 2000, without even having to evaluate it, I know that since it is an even exponent, with our pattern for powers with base 5, it will end in a 6, 2, 5. There we go. All right, a pattern. All right, we found the pattern, and we just had enough to know even or odd, and it makes our life a lot easier. I love patterns. All right, last type of question I want to do. Sometimes we'll be given visual patterns, and you'll see, say, what will be the 79th term in this sequence? And again, just like the first question, we don't want to have to write out all 79 of these shapes, right? That would take way too long. There's got to be a simpler way. We can't really do a T-chart because we're not involving numbers here, right? Like red circle, pink circle, blue triangle. So let's write our term number above. 1, 2, 3, 4, 5, 6. And you know, when I don't know how to start these questions, oftentimes I'll just continue extending it for a bit. So 7, 8, 9 would be big circle, little circle. I won't do colors here. Triangle. Do we notice anything? Well, I notice, looking at this, that every third shape is a triangle. So that means that I know that my 12th shape will also be a triangle, and my 15th shape will also be a triangle, because every third is a triangle. And I can use this to help. So 79th term. What is a multiple of 3 that's close to 79? What would be close to 79 that is, well, I think 81 is a multiple of 3. So I know that 81 is going to be a triangle, right? Because every third shape is a triangle, and 81 is a multiple of 3. I can then just work backwards. 80, 79. So before a triangle is a small circle, so 80 would be a small circle, and before that is a big red circle. So I know that my 79th term will be a big red circle, just by knowing that our pattern repeats every third. All right, every third shape it repeats. So every multiple of 3 we know will be that last shape, which is a triangle. And then we can just work back a little bit and find our answer. So I hope you enjoyed these questions and working through these together. In the link to this video, you can find a link to, in the description of this video, you can find a link to a worksheet that has lots of questions that you can practice that will help, and it also has solutions for them. You can find other videos in this series about problem solving, and make sure to check out Math Fun 101 on Instagram and Facebook.